Hi guys, welcome to homework 21. I'm just going to start now to do the problems that we have for this homework. So let me share this, make this a little bigger. So we'll have the very first problem for homework 21. It says, the drawings show, focus on concept question 1. The drawings show 3 situations in which a positively charged particle is moving through a uniform magnetic field B with a velocity V. For each situation, what is the direction of the magnetic force F exerted on the particle? We did something like this in the recitation last time. So we do V cross B, if you remember. So Z is assumed to be coming out, V is going down. So V cross B, move the V line to the B line, V cross B. Where are you going? You're screwing in where? The negative X direction. That's for the A part. For the B part is going to be the same because V cross B, V is going up, B is going to the inside the plane. So V cross B, you're still screwing in to the negative X axis. You're screwing towards the negative X axis. So negative X, and in the same direction is 0 because sine theta is sine 0 for the cross product. So it's going to be negative X 0. That's D. So the correct answer becomes D. Then the next problem says at a location near the equator, the Earth's magnetic field is horizontal. So and points north. So an electron is moving vertically upward from the ground. What is the direction of the magnetic force that acts on the electron? So I want to explain this. I just suggested these diagrams to help you visualize what's happening. So the equator is this line in the middle. So it goes around, it's a big circle right in the center when you cut this half open. So that equator has its north, its east, its west, and south. I use this to explain it. So this is like the celestial sphere thing, but just to visualize what's going on. So let's say this is the equator and this is Earth. So this flat circle right here is the equator. It has its north, its east, its west, and its south. So what happens is the magnetic field is pointing to the north of the equator, not the north of the Earth. So that's where you can clarify that confusion. Pointing to the north of the equator, so it's pointing this way. And then an electron is thrown upwards. An electron is going up that way. So what is V cross B? So V cross B will be taking the electron going up across the B direction. Is that okay? So if you do V cross B, so we're going to do that. So let's say this is our north. This diagram is a little bit confusing. So our north is supposed to be where east is here, just to be sure. So this is actually north. This is south is east, north is west, and west is south. So the field is going north and electron is going up. So if I do V cross B will go towards the left, will go towards the west. Is that okay? So I'm going to change this N to west, this S to east, then east to north, west to south. Just visualize it that way. So if I'm going, the B field is north, the velocity is going north, up. So V cross B, I'll be going west. So if I'm going west, that's supposed to be the correct direction for a positive charge. So if I go back to the previous one, because the charge is positive, that is why the V cross B direction stays. But if the charge is negative, the direction will be opposite the direction of your actual V cross B direction. And that's what happens here. So our V cross B direction is to the west, assuming this is going north and something else going up. So I have north and up cross north, up cross north. When I screw up to north, I'll be going to the left, that is west. But because it's a negative charge, the direction correct becomes to be east. That's why the correct answer is east in this case. I hope that is clear. Next, says an electron passes through the rectangular regions that contain uniform magnetic fields B1 and B2. The field B1 is stronger than field B2. Each field fills the region completely. How does the speed V1 of the electron in region 1 compare with speed V2 in region 2? So the speed in a cyclotron doesn't change. So why does that happen? The speed is the same in both directions. So I'm just going to give you an explanation for you to see what's going on. So you know your V, you are doing V cross B. So your V direction and your B direction are perpendicular to each other for you to have that your cross product. Is that okay? So you're always going to have the perpendicular, so you say sine theta, the perpendicular component. Even if they have an angle, you want the perpendicular component to multiply the component of the velocity. So if V cross B are perpendicular, it means your velocity and your force that is produced equals F, V cross B equals F. They are all mutually perpendicular. F is perpendicular to B, B is perpendicular to V. And when you know force and displacement, if V is in the displacement direction, if your force and displacement are in perpendicular directions, you don't have work done. Right? You remember that? So I'm going to explain that here just so you see what happens. So the magnetic force in the figure always acts in a direction that is perpendicular to the motion of the charge. Consequently, the displacement of the moving charge never has a component in the direction of the magnetic force. As a result, the magnetic force cannot do work and change the kinetic energy of the charged particle. So if the kinetic energy is the same, the speed of the particle does not change, although the force can alter its directions as it moves. So the speed is the same in both cases, irrespective of the magnetic field magnitude or the speed or the whatever, or the diameter. All right, that solves that. We go, that was focused on concept 07. Now focus on chapter 21, problem 01 says, in New England, the horizontal component of the Earth's magnetic field has a magnitude that an electron is shot vertically straight up from the ground with a speed of that. What is the magnitude of the acceleration caused by the magnetic force? So they want you to get an acceleration. So they want you to do Newton's law of motion, F equals ma, equates that F to QVB sine theta, which is the force of an electron moving in the magnetic field. So I'm going to put F equals ma here. From here, I get A to be QVB sine theta over M. So if we assume they are mutually perpendicular, because no angle is given to us, so we're just going to assume they are all mutually perpendicular, sine theta becomes sine 90. And then we solve for A. So we'll put our Q, it's an electron with that charge. So it's the magnitude, so we won't put a minus sign. It's just the magnitude. If they want us to get the direction, then we have to use our, cross product or right-hand rule, if you like, to solve the problem. So it's just the magnitude, so we don't put the minus sign, we just put the charge magnitude 1.6 times 10 to the negative 19 times the speed 3.6 times 10 to the 6 that's given times the magnetic field in Tesla that's given here 1.9 times 10 to the negative 5 over the mass of an electron 9.11 10 to the negative 31 kilograms, and that solves the problem to give you the acceleration right here. Okay, next problem, chapter 21, problem 12 says, an ionized helium atom has a mass of this and a speed of that. It moves perpendicular to a 0.72 magnetic field on a circular path that has that radius. So this equating centripetal force. So remember, let me see if I can write that here for you guys to see how this formula was derived for the charge to be m mass times velocity over magnetic field times radius. It's just gotten from simply saying centripetal force mv squared over r equals qvb sine theta. QVB sine theta. So if I make this capital B, so if sine theta is perpendicular, sine theta is sine 90. So if I solve for Q here, V cancels V, I'm just going to get this right here immediately. So this, I'm going to call this a different color. I'm just going to go maybe just, just so you guys know what's going on. So this guy, oh no, not that one. I think it's this one. Okay, let me do this. Sorry about that. I go back to black. Oh, shoot. I just messed up. Okay, this is what I want. Like, not that one. Not that one. Okay, but you guys can see though. I'm just going to let it be black the way it is. So this guy, we deduce this equation from this guy. I'm trying to just color it a different color, but it's fine. So this is the cyclotron motion where the electron goes in a circle. So here we can now get the charge to be that. So if you look at this charge, if you divide by the electronic charge, it's actually twice the electronic charge. If you divide by 1.6 times 10 to the minus 19, so 3.2 is twice of 1.6. So then it is twice of the electronic charge. So the charge of the ionized helium atom is plus 2 electrons. That's what the question is saying. You get the charge first and see how many electrons are inside the charge. Next problem, chapter 21, problem 13 says, in the operating room, anesthesiologists, oh my goodness, use mass spectrometers to monitor the respiratory gases of patients under surgery. One gas that is often monitored is the anesthetic in isoflurane molecular mass. That in a spectrometer, a single ionized molecule of isoflurane The charge is given, the mass is given, moves with certain speeds. You're asked to find the magnitude of magnetic field. So since it's moving a circular path in the magnetic field, you're going to just use this centripetal force formula we derived. So B becomes mv over qr, and you just put your things there and you get your answer directly. Mass, speed, charge, radius. Okay. Next, a charged particle, that's chapter 21, problem 15. A charged particle enters a uniform magnetic field and follows the circular path in the drawing. The particle's speed is 119 meters per second. The magnitude of a magnetic field is 0.771 Tesla, and the radius is given. So determine the mass. So the same thing, the mass is QBR over V, just the same. The same, okay? Okay. They are not asking for the direction here, so we don't need to worry about this other diagram, but it's okay. Okay, that's chapter 21, problem 15. Let's go to chapter 21, focus on concept question 11 now. So more focus on concept question. So it says, the drawing shows a current carrying wire lying along the x-axis. So this drawing, this one is just showing the right-hand rule of doing the current times, you know, cross I cross B or L cross B, if you like. I and L are in the same direction. So I cross B, when you have a wire, if you have a charge, it's V cross B. If you have a current flowing in a wire, it's I cross B that gives you the force on that wire. So we're going to cross I and B, whatever direction we screw is going to be our direction of the force on the wire. We're going to use this a lot. Or if you want to use the right hand rule, you put your I to your thumb, your B, your other side, then wherever your right palm is facing will be the palm, the direction of the force on the wire. So we are given the current, we are given the direction of I to the x-axis, B to the z-axis. So what is I cross B? So I cross B, if I do I cross B, I'll be screwing out. I'll be screwing out. Is that okay? I'll be screwing out. So right here. So since I'm screwing out, that's going to be the direction of my force. That's negative x-axis. How do I calculate the force? Now I do the I cross B, IL times B sine theta. So they are mutually perpendicular since no angle is given. So it's just ILB. I is given to be 3 amperes, 0.42 meters, L2, B2 Tesla. You just multiply those, you get 2.52 newtons for the force, and the direction is I cross B. So for the current and data, we don't, and the magnetic field, we don't care about the charge. It's not like a charge that you can see if it's positive, it goes in the direction of V cross B. If it's negative, it goes opposite direction of V cross B. If it's a current, it just goes in the direction of I cross B, no going in the opposite direction. Okay, that's focus on concept question 11. Let's go to the next question. Focus on concept question 14. A square current carrying loop is placed in a uniform magnetic field P. The plane of the loop perpendicular to the direction of the field. The dashed line in the X is in the axis of rotation. The magnetic field exerts. Okay. So we want to see if we're going to have any rotation around this axis. Is that okay? Around this axis. Is that okay? So the magnetic field exert what? So do we have a net force, a net torque, one of each or both? So that's the question. So here, if you go here with the right hand rule, when you go like this, you put your right hand, you go like that, the current is going in your thumb, it goes out of the page on top, it goes inside the page at the middle of the square. It goes like that, okay? Now, when you put it at the bottom, it goes out of the page at the bottom and comes inside the page. Is that okay? Like that, and comes inside the page at the top. So you have a force going in this direction. Is that okay? So if you do, let's say I cross B, for instance. So I cross B, let's do I cross B. Say B is coming out of the screen. So I want to get the force. Let's just do the force first. I'll come to the torque. So I cross B would mean I going this way, B going out of the page. So I cross B, right out of the page, I cross B, I'll be screwing out. So I'll be going down. So this is I cross B, I cross B, I cross, so I'll be going down. Then, but down here on this side, I have I this way, B coming out. So I cross B will be coming up, I'll be unscrewing up. So I have two opposite forces, one down, one up. So those two forces would cancel each other. Then for this guy on the right-hand side, I going down, B coming out. So I cross B, I cross B, I cross B will be going to the left on this side. So if I do this, I'll see to be going to the right. The both forces cancel out. So because both forces here cancel out, is that okay? And both forces here also cancel out because this one is coming down, this one is going here. So there will be no net force at all. And we won't have any torque at all because the forces are not in opposite direction, as in are not in the direction, how do I say it? They are not in a direction to cause a torque. They are all coming to the center. This one is coming to the center. This one is coming to the center. You cannot cause rotation that way. So if one was coming out of the page, if maybe B and I were oriented in such a way that one is coming, the force at one end is coming out of the page and the force at the other end is going inside the page. So the net force will be zero, but that force can cause a torque. But in this case, we just have them coming to the center and out of the center, so we can have a torque. It's like a force trying to compress this wire and they cancel out. So the correct answer becomes B, neither a net force nor a net torque on this loop. Okay. Next problem. So suppose you wish to construct a motor that produces a maximum torque whose magnitude is this. So for torque is number of turns times current times area times B sine theta. Maximum means sine theta goes to 1, so theta is 90 degrees. So maximum torque is just NIAB, so you can get N from there to be maximum torque over current times area times magnetic field. And you are given everything there. So just put your maximum torque here, your current, your area, your magnetic field, and you get your number of turns. It has no unit, it's a number, so it's just 86. Excuse me. Okay. That's question 15, focus on concept. Now let's go to focus on concept question 16. So the drawing shows 4 situations in which 2 very long wires are carrying the same current, although the direction of the currents may be different. The point P in the drawings is equidistant from each wire. So which one or more of these situations gives rise to a zero net magnetic field? So the magnetic field is your right hand rule. So take your right hand. For number 1, the current is going this way. To the right, so magnetic field is called that way. So at P, your magnetic field is going inside. For number 2, your current is going this way. At P, your magnetic field is also going inside. So question 1 has magnetic fields summed together. So you not have 0. For number 2, they're in the same direction, so you can already guess. So going like this, at P, magnetic field goes inside. Going like this, at P, magnetic field comes outside. So going inside, coming outside cancels out. So 2 we definitely give 0 magnetic field. Then let's see 3. 3 will not give because at point P for the first one is going inside. For the second one, at point P, for the first one, at point P, it's going inside. For the second one, at point P, it's also going inside. So both of them will combine. You don't have 0. Then for 4, going to the current going to my thumb, I fold my hands. So when you fold your hand, you just have to see how this works. The top of your hand is how it comes up. So coming out is on top of the wire. At point P, your fingers are coming in. So it's going to go on top of the wire. If point P was at the top of the wire, it will be coming out. But because P is below the wire, then your hands are already called going in. So don't confuse this. Then for this guy, my current goes up. At point P, I'm coming out. If P was to the right of the wire, I'll be going in at that point, but coming out. So coming out, going in, cancel each other. So it's 2 and 4 that has 0 net magnetic fields in this case. Focus on concepts. Question 17 says, 3 long straight wires are carrying currents that have the same magnitude. In C, the current is opposite to that in A and B. The wires are equally spaced. Which wire experiences a net force due to the other 2 wires? Okay. So you want to know the net force between 2. Is that okay? Okay. Okay. So here we know when we have 2 wires, we're going to take 2 at a time. When we have 2 wires with current in the same direction, what happens? They attract each other. Opposite direction, they repel each other. So these 2 are in the same direction. So the force on B due to 1 will be going this way. The force on B due to this opposite direction is repelling. It will also be going this way. So B will have a net force going up. But A and C are in opposite direction, but their distance is more. So it will be repelling, but not as much as between these two. So the one that's going to experience the highest force is going to be B, because it has force from here and force from there, and they both sum in one. In that, okay. So in opposite direction, so this one is gonna, in opposite direction, they repel. B is gonna repel C, A is gonna repel C, but the repulsion from A is not as big as the repulsion between B and C because of the distance. So you have to always, worry yourself the distance of separation. So B is the correct one because it has the shortest distance with two force summing together. So it's gonna be the highest one. Okay, the next problem, excuse me. It says, focus on concept question 19. Two circular current carrying loops of wire are shown in the drawing. The inner loop has a radius of R0 and carries a current that I0. Outer loop has a radius of 2 R0, carries a current 4 I0. The currents are in opposite directions, as you can see. So you are given R0 to be 2 meters, I0 0.2 meters, I0 to be 1.6 amperes. So they want the direction and magnitude of the net magnetic field. So in a circle, the magnetic field at the center of a circle is given by a number of turns, mu0 I over 2R, but they both have just one turn. So N is just one. So for the inside circle, I call BI, the internal circle. So it's going to be mu0 I0 over 2R0, because that's what we are told. The current is I0. The radius is R0. We already have a 2 from the formula, so 2R0. And the magnetic field for the external one, the bigger circle, is mu0. The current is 4I0 over 2. R is 2R0. So it's going to be 4R0 now. So 4 cancels 4. I just have mu I0 over R0, and that is just twice B internal. So B external is twice B internal. But since the current are in opposite direction, let's think about the directions now. We've gotten the magnitude. So what's the direction? So right hand rule, this one is going up, the internal one, current is going up that way. So when I fold my fingers, my finger in the center will be going inside. So B internal is into the screen in direction, and B external is going down. My same right hand, I go like this at the center to be coming outside, out of the screen. So since B external is twice of B internal, so outside of the screen is going to win the net. So the net is going to be outside of the screen. So it's going to be 2BI minus BI. So my B net is 2BI minus BI, because 2BI, the external one, is coming out of the screen. So I calculate 2BI minus BI is just BI, which is this guy. So I put mu0 I0 over 2R0, 4 pi 10 to the negative 7 is mu0, I0 is given 1.6. I put everything in there, and I get my net magnetic field out of the screen. Okay, let's go to the next problem. Chapter 21, problem 31 says a 51 meter length of wire is stretched horizontally between two vertical posts. The wire carries this current, experiences this magnetic force, and we have to find the magnitude of the Earth's magnetic field. So we're just going to use F equals IL cross B, or ILB sine theta. So B is F over IL sine theta. We are given the angle with respect to the wire that the field makes with it. So we'll just put everything in there to get the force divided by current times length times sine of theta. Chapter 21, problem 48, go. You have a wire of length that making a square coil of a DC motor. The current in the coil is given to be that, the magnetic field is given. You're asked to find the maximum torque exerted on the coil when the wire is used to make a single turn square coil. So it was a length wire, you make that wire into a square. So we know that maximum torque is NIAB sine 90 degrees, which is 1. So it's just NIAB. But how do we get the area? It's a wire you made into a square. So for the one that is the square, just one turn, a square, is going to be NI. The area will be 1/4 of the length of the wire, because if it's a square, each side will be 1/4 of the total length the wire was. And a square, one side square is the area of a square. So 1/4 L squared is our area, and you solve that to get the maximum torque. But the number B question is 2 turn square. So you now make 2 turns of the same wire. So the square will be smaller because it has 2 turns. So what will be each length? Each length will be 1/8 of the original length before we made the first square. So our area will be 1/8 of the original length square. But now we have 2 turns, and then we do the same multiplication and we get our answer here. So this is the trick to solving this question. Okay, chapter 21, problem 54. A long solenoid has a length of this and contains 1500 turns of wire, and we have the current. We just find the magnitude of a magnetic field. For solenoid is mu naught times number of turns per unit length. That's the small n times current. So number of turns per unit length multiplied by mu naught times current, and you get that. And then the last problem, we're asked to find number of turns per unit length. So it's a B over mu naught I, just the opposite of what we did, and pretty straightforward. So thank you guys. I'll see you guys next week. Have a good one.